Hello everyone, my name is Ilias from National Technical University of Athens, and today I will present you our study in the investigation of physics-based transformers in tsunami predictions. Essentially, tsunamis are a devastating physical phenomenon which is very hard to predict because it's very computationally intensive and needs plenty of computational power and time to have an actual result. And the last 10 years, it's very popular among the research community to apply AI in this problem to speed up the process or help the computational algorithms speed up the process by handling some parts or computations. In this study, we will investigate the effect of inserting physics into AI models. These are called in the AI community physics-informed models or physics-based models, which essentially means in the stochastic training process of an AI model, you insert some physics-based rules to guide this process to a certain direction. Our dataset that we use in this study consists of 3,000 simulations of earthquakes in the Tofino area of West Canada, which Professor Goda has run recently by using magnitudes between 8.2 and 9.2. And essentially what we have is 26 offshore locations in different parts of West Canada and the Pacific Ocean, as well as 36 onshore and nearshore locations in the Tofino Island. Here we see some of the main offshore buoys. These buoys essentially are stations in the middle of the water that record the wave height and the wave speed in these offshore locations. And in the other part, we have the 36 locations in the Tofino Island, which we have the wave height and wave speed recorded as well. And essentially, what we're trying to do is, by giving the input from the offshore locations, is to try to predict the onshore wave speed and wave height. The input of the model looks kind of like this. Essentially, it's a waveform with 3 hours of duration, and is recorded in the 26 station as a time series, and we have both the wave height and the wave speed. And we try to predict the same wave speed and wave height in the nearshore and onshore locations. The model that we used is a transformer. Transformer is a very powerful model which is used in many areas recently, even in language models such as ChatGPT, vision problems, computer imaging. It's a state-of-the-art model, and we try to apply it in the prediction problem using physics-based solutions. Essentially, the physics solutions we tried is to, apart from giving the whole waveform as an input from the offshore stations, we inserted some physical characteristics. The two characteristics that we inserted is the physical distance of the stations. So we insert some geospatial logic in our model. And the second variation we tried is to, apart from just giving the distance to the model, we also give the travel time. And this inserts the logic that stations that are very far apart don't have a very strong connection between them, because won't have that much of an effect to have a very big travel time. So closer connections and closer distances, insert a bigger connection, let's say, between the weights of that pair of offshore and nearshore locations. Also, that characteristics insert a physical causality that the waves travel from offshore to onshore locations, which is a physical law and a logical law, of course, of the waves and the wave travel times. Here we have the results. We train the model by using 70% of the dataset as a training set, 15% as a validation set, and 15% as an independent test set, which was used in the end to test the model independently without inserting any bias from the training dataset. Here we see two pair of lines. The first pair is the wave height with blue, which is the ground truth, and with orange we see the predicted wave height for the station 0, which is a random station we chose. We see that our model have a very similar prediction as the ground truth and matches the peaks and ups and downs in some parts. Also, in the bottom part we see the wave speed, which is with green the ground truth and with red the prediction, and again we see that our model matches the corresponding ground truth wave speed. And essentially we see in all of the examples that the model can accurately predict both wave height and wave speed, which is a very crucial thing when calculating momentum and potential damages and effects of inundation onshore. Finally, in the conclusions, we see that our transformer can predict accurately both wave height and wave speed, and specifically wave height is easier to predict compared to wave speed, and that's because even when we don't have large wave heights recorded in the buoys, we have a constant flow of water, so we have constant wave speed, which makes it harder to predict. Second of all is that apart from having wave height it's easier to predict, is that the physics-based transformer that we tried showed better performance compared to the normal one. So we deduct that by inserting the physical characteristics we improve the performance of the model, and also we exclude illogical and improbable values that laws of physics doesn't let to occur in nature, such as negative speed and this kind of results to occur, and this can be done easily by inserting the physical restrictions. And it shows a prominent solution for predicting fast and accurately wave height and wave speed. And if you pair it with a other study for the early warning model, it can act as an early warning system to alert imminent danger in those areas. Thank you for your time.